Okay, so let's get started. We are at the end of the first part of the module on the physics of atoms. The first part has to do with a hydrogen atom, but we add in many of the details. We have done so far spin-orbit interaction, the Zeeman effect, in experiments that has to do with the hyperfine, the fine structure, and then the splitting of spectral lines in a magnetic field. We also have done the Zeeman effect twice. First, ignoring spin, and then later on, we have spin in it, and then we study the strong field limit, which give us the normal Zeeman effect, and the weak field limit that give us the enormous Zeeman effect. Last time we started the discussion on the very last topic on the hydrogen atom, those fine details. It is about hyperfine structure. It is related to the fact that even the nucleus, the proton, has spin. Proton is a fermion, it has spin half. Thereby, even if we don't consider the effect of motion, we still have a two-particle system with the protons being spin half and the electron being spin half. Last week, well, 2 weeks ago, we learned how to add two spin half entities that will give us S equals 0 that we call spin singlet, and S equals 1 that we call the triplet. So the question becomes, in a hydrogen atom ground state, we know the electron is in 1s, so there's no orbiting effect, but it has a spin half. Usually, if you don't care about the proton, the nucleus, this 1s state, you may think that it has an up spin state, down spin state, and they are degenerate. But now we have to include the spin half of the proton if our precision measurements really down to that fine details. Then the question becomes whether the singlet alignment, where the two spins tend to be anti-aligned, or the triplet alignment, where the two spins tend to align, have which one has the lower energy? Okay, so that is the question. So let me pick up from there, and I just want to introduce the key physical picture and idea. So last time we introduced that the proton has spin and it has a positive charge E plus E. Therefore, it also has a spin magnetic dipole moment. So you may think as two magnetic dipole moment now interacting with each other. In this idea, it is easy to imagine that you have a dot product. You have a mu n dot into the nuclear magnetic dipole moment, dot into the electron's magnetic dipole moment with a minus sign in front. Thereby, if they align, they will be happy, things like that, okay? So with this dot product thing, that will give us the dot product of the two spin angular momentum. The subscript P refers to the proton, the subscript E refers to the electron, but both are spin half. So thereby we have this classic situation of adding or coupling two spin half angular momenta. And if we divide by h bar, it is just a way to make this a number because angular momentum has the natural unit of h bar. You divide the angular momentum by h bar, that becomes a number. For example, square root s times s plus 1, right? That is the magnitude. With the h bar, then it gives you the natural unit. And this is meant to be an interaction energy. Therefore, we have put all the energy stuff in the prefactor A. We will not go into the details of what factors compose this factor A. I just give you a ballpark order of magnitude. So at this point, it will be useful to remind ourselves two pieces of physics. We need to handle this kind of coupling of two angular momentum. This is not the first time we did that. This is the third time actually. So the first time we did such a situation is a S dot L. And we know how to do that. We better define a total. So in our context now, we should have a total spin angular momentum. So in the previous situation, we have S plus L. The second step is to dot into yourself. So J square is S plus L bracket square. Therefore, you will pick up a cross term. And we need this cross term. So we copy through, we will have S proton dot into S electron being the total square minus proton spin square minus electron spin square divided by 2, something like that. Okay, so in this first step, we know what to do. The second thing is that we are adding 2 spin half, thereby, based on what we learned before, we would expect 2 results. One is a spin singlet, one is a spin triplet. Okay, so one is S equal 1, one is S equals 0. There is 1 state here, there are 3 states here. Okay, and that corresponds to 4 total states. 2 spin, you can have up, up, down, 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 up, down. Okay, but there are linear combination of this down, up, down that makes up this triplet MS equals 0 and singlet state. So with this background, we can actually carry out the hyperfine structure discussion. So we have such an interaction term, the dot product of the 2 spin of proton and electron. With our experience, we better define a total. Then we square it, therefore we will pick up a cross term. So we are copying the idea through, and that will be J square. In our context, that will be the total spin square minus proton spin square minus electron spin magnitude square, okay? But both are spin half, therefore it's a boring 3/4. This is half times half plus 1, okay? And then electron also spin half, so they're the same. This S can take on 0 and 1. Therefore, with this coupling, the S equals 0 singlet state will have a different energy, slightly different, okay, but different energy than the triplet S equals 1 state due to this term. You plug S equals 0 into it, it is 0, therefore you have some number, and you plug S equals 1, this is 2, this S plus S times S plus 1, therefore it will give you another number, a bigger number. So you see there will be a splitting of the energy due to this nucleus spin and electron spin coupling. So with this idea, immediately we know this hyperfine interaction term. We better use the total spin as our good quantum number, so-called, and we know that S equals 0 and S equals 1 will give us 2 different eigenvalues. Okay, there is a factor A that defines the strength, how strong this effect, or actually how weak this effect is. So it is the same as the spin orbit interaction concept. Now we plug in S equals 1. This whole factor gives us a plus sign, plus 1/4. And if we plug in S equals 0, this whole thing gives us a minus 3/4. This is a very famous result, especially for those who want to go into condensed matter physics and try to understand ferromagnetism, why we have magnets. And you will see this 1/4 and minus 3/4 come out again and again. But let's get back to our context. There is a prefactor A here that sets the scale, how strong this hyperfine structure is. Therefore, there is a A/4 that is the triplet state, S equals 1. There is a minus 3A/4 that is the singlet state energy. So we immediately see that there is a shift in energy according to whether the two nuclear, the nuclear spin, the electron spin tend to align or tend to anti-align. Okay, this is S equals 0 basically, and this is S equals 1. Okay. Here, I have been using the most common notation. Common means easier to understand notation. But in the literature, the total spin, usually for this particular hyperfine situation, is not called S. Instead, it is called F. But I don't want to introduce a new symbol so too soon, just to use our old knowledge to handle it. It is only a notation problem, okay? So I get the physics through first. So now we have the conclusion. Indeed, proton spin, electron spin, they interact, that is a fact. Usually we don't need to care about it because soon we will see how big this A is. This is weaker than weak. That's why it's hyperfine. Fine structure is already 10 to the minus 5, 10 to the minus 4 eV scale. Okay, so this is even 1% of that. So something like 10 to the minus 6 eV. Unless you really need to care about this detail, or you have apparatus that can measure this tiny difference. So usually in astronomy books, you have to understand this effect. Usually it is done in a very pictorial way. So I copy those pictures out from astronomy context. So those books will tell you, this is the proton spin, this is the electron spin, okay? The question is whether this or that has a lower energy. Now we know how to handle it in quantum mechanics. Indeed, the triplet state, S equals 1, has a higher energy. The singlet one has a lower energy. Here in astrophysics book, you may see the usual notation using the F as the total spin of proton and electron. Okay, but it is the same physics. And now let me introduce the name. This is hydrogen 1s. Originally, it is an up-down degenerate if we don't care about proton spin. Now, with this tiny, tiny detail in, there are two states splitted. Therefore, this is called hyperfine splitting. Okay, so hyperfine structure refer to this, the effect of this splitting. Can we see it? Yes, we can. Every day, the astrophysicists are using this to survey the sky, so-called survey the universe, the interstellar space. There are hydrogen atoms there, very dilute. Therefore, there are atoms there. Of course, in addition to molecules, when they meet, they may form H2 molecule. However, the concentration is so dilute that there are many neutral hydrogen atoms out there. So this is called the hyperfine splitting, all right, or hyperfine structure of hydrogen atom. So now we want to look at how fine is this hyperfine splitting, or how small, I should have said, how small, but not how big. So that has to do with the prefactor A, which is an energy, the energy scale of hyperfine structure. Here, I could not derive it for you here. It is out of the scope of our course, but I just would like to give you the ballpark number. It has to do with the mass of proton and electrons, Bohr radius, and then there's a G factor for proton, which is about 5. For electron, it is 2, and then for proton experiment give us the number that is about 5 point something, or the 1 anyway, h bar to the 4th. So we plug into it all the constants. Well, it is a combination of constants, okay? And then it is about 10 to the minus 5 eV. We have a 6 in front, okay? So give it more generously. So it is something like 10 to the minus 5 eV. So it is like a 10% or a few percent of the fine structure. And now, if we use this number and look at the splitting, therefore, this is A, okay? Therefore, this splitting refers to this particular energy. And energy can be represented as a frequency, because if there are light or photons of this frequency around, the hydrogen atom will absorb it and excite itself from here to there, okay? And then later on, because it is higher energy, it will be de-excited and then give out the photon, all right? So therefore, it will be nice to look at what is it in terms of frequency. You calculate it out, delta E divided by the Planck constant. It is the famous 1420 megahertz. Now, this is one of the numbers most accurately measured in physics. This is the latest number, I think, okay? So it is a very accurately known number. It is in the microwave range, all right? You know, there's some microwave background outside there, referring to about 2.7 K in temperature, okay? So that is related to why astrophysics, they will use this particular hyperfine splitting. So this is a number that worth remembering for physics students. And the corresponding wavelength, you can again calculate it using the speed of light. That is the very famous 21 centimeter line of hydrogen. Again, 21 centimeter is about that big. It's easy to visualize what it is. Your microwave oven is about that big. So it's again microwave wavelengths, okay? So if we put all the things together up to now, without the hyperfine splitting, we have the relativistic correction, spin-orbit interaction. We have this result. QED give us some more result that we cannot explain it to you. This is quantum field theory. It's shift a little bit called the Lamb shifts that has to do with what is vacuum. But now with hyperfine, even this ground state of hydrogen, now this is highly exaggerated, I must say, okay? Just to let you know that there is something there, all right? So not to scale, absolutely. So what we have seen is that there will be a hyperfine splitting of the ground state of hydrogen. We can carry out similar discussion for all the other states. Okay, so you will see the different states. And here, actually, you will have to use the total angular momentum by adding the 3/2, which is already L plus S, into spin half. Okay, therefore, you will have 1.5 plus half, which is 2, 1.5 minus half, which is 1. Okay, so this is the hyperfine splitting. But the most important effect has to do with the ground state, this 21 centimeter in line. This page is just for those who have read this, who have read about this in astronomy course. You may encounter a different notation. So the proton spin will be, the nuclear spin will be I. The electron total angular momentum is J that we used before. And now they couple and the total will be called F. So you will see a different symbols, but the physics is just what we discussed. So this page is just meant to make connections, especially for those who have taken some other courses. An important sign for this hyperfine splitting is that actually the SI unit of time is related to hyperfine splitting, but not in hydrogen. If you go from the periodic table, hydrogen, lithium, and then sodium, potassium, go down. Down the column, there is a cesium atom. And its structure is 6s1. So it goes down to rather down in the column. The reason for using this is that the hyperfine structure is measured even more accurately. So this is the number, okay, that many labs in the world can easily reproduce. And therefore, I will go back to that later. This number is now being used to define a second. So if you look at the SI unit definition, it has been changing. Most recently, in 2019, May 20th, even the definition of a kilogram has been redefined. Now, it is redefined using an accepted number for the Planck constant. So even a kilogram. So you go to the supermarket to buy bananas, anything, suddenly it is quantum defined. You need the Planck constant to define the kilogram. Of course, in daily life, nobody cares about, I think very few people even know the kilogram has been redefined in rather recently, right? Less than 2 years ago, okay? The reason is that now H has been repeatedly measured up to a required accuracy. There is a conference called IUPAP, International Union of Pure and Applied Physics. So they usually meet every 3 years or so, and then see whether we should update the definition of SI units. And then for kilogram, actually they have been thinking about it for about 10 years. A few years ago, they set a criteria. If by 2017 or so, there are more than a certain number, maybe 3 different cases, that confirm the accuracy of the Planck constant up to a certain number, then that will be more accurate than the kilogram. In Paris, they have kept a piece of stuff, weight a kilogram. Okay, that has been there for 200 years. More than that, I think it's around 1790 or something, the French Revolution time. Okay, so at that time, they start to define the SI unit. SI means Standard International. So it is international system international. So it is international system. So originally it's from France. So in Paris, they have kept this piece of kilogram as that is the standard. And then they have a few reproduction sent to other standard labs. That has been used for many, many years. And only recently, physicists found that if H is sufficiently accurate, then we could replace that piece of stuff called a standard kilogram by using H, and together with some speed of light, 1 second, then we can combine it to form a kilogram definition. And that is now in use, okay? Of course, you will not feel that in the market. So radio astronomy has to do with surveying the sky, try to see this particular 21 centimeter line, okay? Now, one thing to notice is that, say, room temperature, 300 K, okay? It refers to 0.024 EV, okay? This is 1/40 EV. That is a good number to carry with you. You need to do thermal physics, you need to do statistical physics, right? This is a number that you should know. Therefore, if you think about what is 10 to the minus 6 EV, it is 0.07 K. And that is good, because out there, we have 2.7 K. That is so-called microwave background. So that is a bath in which the hydrogen atom lives. Therefore, not all the hydrogen atom will stay in the ground state, the singlet state there. The bath will be sufficient to thermal excite some of them up here. Okay, it is a dynamical process. Some go up, some go down. Actually, this transition is a very slow process, meaning the lifetime is very long. It doesn't happen very often, but we have a lot of hydrogen, neutral hydrogen atom out there. Okay, and that is why the astrophysicists can survey the sky, look for this 21 centimeter line in different locations, especially around galaxies. And by Doppler's effect of this 21 centimeter line, we know that some is coming towards us, some of it is going out of us, thereby we can reconstruct beautiful pictures of this spiral galaxy. I took this picture from the European Observatory. And latest development is that last year, January, in China, Guizhou, that is the biggest, well, at this moment, the biggest radio telescope on Earth. This is the 500-meter aperture radio telescope. It's called shorthand PHYS. They started to operate, and I think they have done some good work in discovering more pulses. Okay, but if you look into their website, I encourage you to do that. Then, because they need to argue for the funding, why this thing should be funded, built, and so on. So they have some scientific mission. They list out, okay? The very first one is to do large-scale neutral hydrogen survey. And this is about the hyperfine structure that we mentioned. It just started, okay? So let me end this part with a few questions, okay? I'm not going to answer them for you. What is the effect of a finite mass of the nucleus? That's easy, right? Reduced mass, nice. And then we do have deuterium, right? So not only proton, but a proton-neutron forming an isotope of hydrogen. So we can use deuterium again to do very precise spectroscopy. And a very interesting, and I think up to now it is still a debating question, is how big is the proton? So this is a very good scientific question if you think about it. Proton, after all, electron, proton, neutron, are the first few particles found, right? This is subatomic. But up to now, we are not so sure about how big is a proton. We are quite sure that it should be something like 0.8 something from Fermi, meaning I think 10 to the minus 15 meter. Okay. So we are quite sure that it is 0.8 something something. But the problem is, what is that something something? All right. And there is something that actually undergrads can try to investigate for themselves periodically. For example, you know some electromagnetism, right? So if you imagine the nucleus is not a point charge, but is a uniformly charged sphere with a radius r, okay? And suddenly, you also know, if you look into Griffin's electrodynamics, you also know what does this finite size nucleus provide as the potential energy function into the Schrödinger equation. It will give you a potential energy function like this, okay? Outside the sphere is just the usually Coulomb, because outside there you see the whole thing. But if you go inside the sphere, you only see some of them, so it's not the Coulomb anymore. Therefore, if the proton is like a finite size sphere, there will be some effect to the transition that you can observe. For example, 2p to 1s optical transition, the length shift due to the vacuum, the quantum electrodynamics effect, or even many people look at the 2s to 1s, that is forbidden, so-called, but it is forbidden for one mechanism, electric dipole mechanism. But if you do something else, something called two-photon transition, that is still observable, okay? So people have tried that. constantly. So you can look up the literature on this problem. It is still not settled. You may wonder what is why is there an effect? Okay, now you have learned the hydrogen wave functions last term. So you have plot those 1s, 2s things out. Okay, so you look into the hydrogen wave functions, especially something called the P of R, the radial probability density. Do you know that? Okay, so 1s, something like that. 2s, there's a bump near the nucleus. Okay, now if you look at 2s wave function, it has a bump rather close to the nucleus. Thereby, if the nucleus is a finite size of different, even slightly different sizes, there will be some effect. You can use perturbation to do it. Okay, that will affect states like 2s, 3s the most, because there is a bump near the nucleus for this S state. And even physicists are very clever. They use muronic hydrogen. What does it mean? A proton and electron, that is a hydrogen atom. But how about this? I don't use the electron. I trap a muon. Muon is an elementary particle, the cousin of electron, but it has heavier mass, something like 300 times or so. So everything, it looks like an electron, but just the mass is bigger. Okay? Thereby, the Bohr radius will be smaller. The wave function will be closer to the nucleus, therefore will be more sensitive to any different guessed sizes of the nucleus. So that has been done. Experiments on muronic hydrogen. Okay. So here just some final remark. I have another file just to say a few more words. For those who like atomic physics, it's a very hot field now, called AMO in physics. Atoms, molecules, and optics. Okay, so atomic, molecular, and optical physics. So it's now a very hot branch of physics. For those who like to read more, this is a very easy book to read. Undergrad atomic physics, but with some new topics like co-atom, like what Professor Wang Dajun's lab is doing. And for those who like to learn the theory of atomic physics using quantum mechanics to a very far extent, this is a good book by Branson, and the authors wrote two similar books. One is about quantum mechanics, very thick, you can learn everything. And then the other one has to do with atoms and molecules, applying quantum mechanics in great detail. This one is more advanced atomic physics. It's like a beginning, I think, MSc or senior undergrad. This is easier. This is like year 3. I think this is like year 4 or first year postgraduate. And then for those who like the chemistry, the chemist treatment, this is a great book to learn quantum mechanics and atoms and molecules. Okay, so I have a few pages that I would like to share with you. It is just a few pages to give you some links so that you can look at the frontier topics. I list a few here. Another one is the FAST, the radio telescope that you can easily look up because it is the hottest apparatus on Earth now on radio astronomy. Here I list a few, all relied on very accurate hydrogen atom. That's what we learned, spectroscopy, 光谱学. Okay, so even this hydrogen atom spectroscopy has been around for 150 years, starting from this Balmer series, Nyman series, 1870 or so, up to now. Many frontier research is still relying on hydrogen atom, but now very accurate measurements. So one thing very interesting is about whether matter and antimatter behave in the same way. Now, that has to do with why we now are dominated by matter. Why don't we see antimatter, things like that? Okay, so the only antimatter now physicists can produce is antihydrogen. That can be formed, okay? And that can be formed and keep for sufficient long time to do experiments. And that's the important point. Nonetheless, it is not a daily, day in and day out experiment. It is one of the CERN experiments. You know, there's a ring in CERN, you know that, right? CUHK. There are 4 stations, right? So there are different experiments along this ring. One of them is called alpha. It's not as big as the Atlas, looking for the Higgs particle, things like that. It is a smaller collaboration, okay? Not thousands, maybe a 100 smaller scale. But they are doing very fascinating physics. One of them is to produce anti-hydrogen. So they have antiproton, is a proton antiproton beam bomb, okay? So they can produce anti-proton, and now anti-electron is positron. A positron is rather common. Even in the hospitals in Hong Kong, you have this PET scan, so it is positron that has to do positron electron annihilation and then give out some EM ray that you can detect. Okay, so now we have antiproton, positron. If you can trap them, now that is hard, because in accelerator they are moving in great high speed. Now you have to slow them down and then let the Coulomb interaction works and then form hydrogen. And more, they can look into this like a 2p to 1s transition, Lamb shift, things like that, okay? So they actually look at the Lyman lines. They also look at the fine structure. So here I give you a few papers up to last year. So they work out the fine structure of anti-hydrogen. It is a Nature paper that deserves it, right? Up to now, antimatters behave within the accuracy of experiment the same way as matter. Okay, so far. The second one I mentioned already is how big is the proton. Okay, we know that it has a finite radius, so it may be something like this, and it may be something like that. Okay, so you may wonder, why bother? It's only off by 0.03 in 1 Fermi, 10 to the minus 15 meter, okay? But the issue is, we have we believe, physicists believe, very reliable way of doing experimental measurement of the size of a proton. One more traditional way is electron scattering. So in classical mechanics, you have learned this problem. You have a central force center, something comes in because of the interaction is scattered, right? Okay, so now again, you can think about it as a finite sphere, and then electron comes in, you study how electron is scattered by proton, you can infer the radius of a proton. That has been done for half a century and more, and we believe that is a good way to get the size of a proton, and actually size of other nuclei. That is part of nuclear physics. Everyday people are doing that. But we also believe there's another way, also very accurate, that has to do with spectroscopy. We just mentioned the transitions, the optical transitions. So we have two very reliable methods, and measuring, we believe, the same thing, the proton size. Therefore, we expect they give the same result, at least with error bars. The result should overlap. But the experimentalists carry this thing highly accurately. The error bar has been shrinking, and the two sets of results don't even overlap within the error bar. So there is an issue here, okay? So it has been developing. Again, I give you a few links. Up to here, I think there is a recent paper, right? Okay, so two months ago, there is again a 2-photon measurement that has to do with the 2s to 1s, I think, transition. Again, the issue has not been settled yet. Okay, more experimental evidence is now pointing at the smaller one, I think. It's more closer to this one than the bigger one. Nonetheless, it's not settled. Another issue about hydrogen, of a proton, is that how the proton gets spin half. A very fundamental one, right? Okay, so the issue is that in particle physics, we know a proton is not a fundamental or elementary particle. It has something inside. What's something inside are called quarks, and they interact through gluons. So inside the proton, there are at least 3 quarks and a lot of interacting gluons existing. And the quarks also have spin. So how could we account for this spin half and the observed magnetic dipole moment of the proton starting from what is making up the proton? So this is a very difficult problem. Sometimes this is called the proton spin crisis. How can we understand this spin half stuff using what is hidden inside? Okay, so again, there are experiments, there are calculations, very difficult so-called QCD calculations, because we have to deal with how quarks interact through exchange of gluons. So something that looks very fundamental and simple are still rather hot research topics. Okay, so for those who are interested in this frontier questions, you may click on those links and then start learning a bit by yourself. So I will stop here for this first hour. Okay, so let's take a break, and then I will clean up some question.